So good morning. I am Krishna Kumar from Krishna's classroom. Let us continue with the explorations of the transpose of linear transformations. In fact, we introduced the concept of the transpose of linear transformations in the last lecture. We also proved that we also investigated in the finite dimensional case the relation between the matrix representation of T and the matrix representation of T transpose. And we found that these two matrices, when they are related to one another through the dual basis, are in fact connected by the relation that the matrix representation of the transpose is essentially the transpose of the matrix representation of T. I mean, this was a very important result. Of course, there one should consider, one should realize that, we start with certain ordered basis for the domain space and the range space, and then for the dual spaces we take the dual basis, and then it is with respect to the dual basis that we are writing down the matrix representation for the transpose transformation of T, and then they are connected through this relation. So let us just recall some of the things that we have. We have VW, V and W as vector spaces over here. At the moment we are not saying anything about the dimension, but in some cases we have to specifically make a mention of it. Let V prime, W prime denote their respective dual spaces. Let E be a linear transformation V into W. Then we have the following theorem. This is what we have. For each linear transformation, T from V into W, there exists a unique linear transformation T prime from W prime into V prime such that T prime G of B equal to G of So this is a crucial relationship that connects T with T prime, or that defines T prime. And we have indeed proved that such a linear functional exists, and that linear functional we such that G of TV equal to FV. It's a linear functional, and then we also defined T prime as by T prime of G equal to F, and then we proved that the mapping that we have defined from W prime into V prime is a linear transformation. Okay, so this is the picture that we had connecting all of them. You have V, W, and you had V prime, W prime over F, and this is what you have, V, there is this T connecting the T here. Now you have a G belonging to, for a G belonging to W prime, G carries TV to a scalar called G of TV, and G belongs to W prime. Now what one has is, you can describe this as f of V for some f, and that f turns out to be in V prime, so that f, this is that particular f, and we define T prime by T prime of G equal to F. This is the definition of T prime. And GF belongs to V prime. Okay? And then what it does is that you have, this is equal to T prime G of this is the connection, and this is the scalar that you have. So this is how these two operators or linear transformations T and T prime are connected. That is expressed in this theorem. This we have already explored. We even explored the matrix representation of T and the matrix representation of T prime. Okay, so let us just recall that. Now further we have proved the following. If BV is an ordered basis okay. What we have done is, here we assume that both V and W are finite dimensional. Now assume are finite dimensional. And we take n to be dimension of V and m to be W. Then dimension of V prime equal to n, dimension of W prime equal to n. So here BW equal to W1, W2, etc. Wm be ordered basis of V and W respectively. Let B prime V be the dual basis of V prime dual to V and BW prime the dual basis of W prime dual to V W. That is, we have Fi of Vj equal to delta Ij for I comma j belonging to n, and Gi of Wj equal to delta Ij for I comma j belonging to then what we have proved is the following. Then A is defined by A denotes the matrix representation of T with respect to the basis, ordered basis BB, BW. Say belonging to F and B T prime in relation to BW prime, comma BV prime, which belongs to M N by M F we have the following connection between these two. A transpose where A prime is the transpose matrix that means row and column interchange. By interchanging the column so this is the connection between the matrix representations of T and T prime related to the dual basis. Okay, so this is what we have proved. Now what we propose to look at some more properties of the T prime and T. How these spaces and their ranges, their domains, their null spaces, all these are interrelated. Okay. Before that, we just recall the thing. We recall the concept of annihilation. Let V is the direct sum of two subspaces M and N. Then we have the following. So let annihilators of M and N respectively defined by M naught is a subspace of V prime, okay, which is equal to the set of all F belonging to V prime such that F of equal to 0 for every V belonging to F. That's the definition. Likewise, N naught is also defined. That's an obvious way how it is defined. Now this we shall need, or this notation we shall need for the rest of the developments. Now let us just come back to the same picture. Now you see that the range of T is a subspace of W. And this has an annihilator. Okay. So you range of T annihilator is a subset or a subspace of W prime. So what do we have? Range of T is a subspace of W. And null space of T prime, okay, range of T, annihilator of the range of T is a subspace of W prime. Then we have, if you take the null space of T is a subspace of V, and you have null space of range space of T prime is contained in V prime. Okay. Now what about the annihilator of NT? This is certainly contained in V prime. Okay. And we also have the null space of T prime is contained in W prime. All these results, all these identifications we have. Okay, so I come to that. So this is RT null space. Okay. Now you have the null space of T, and then you have the annihilator of the null space of T. Okay. So we are just trying to explore the relationship between these entities, which will give some insight into problem. Okay, what do you expect? Let us take one of them and try to describe this mark here. Okay. Now let me try to explore the relationship and then we will finalize this. Now you see that we have the following connection. So let me roughly look at what is that you expect. Okay. Yeah. So you start, okay, what is the basic relationship between T and T prime? It is the following. That is G of TV is equal to T prime of G this is the connection between, this is how T prime is different. Okay. Now let us observe the following. Suppose G belongs to RT then what happens? If G is in RT annihilator or annihilator of RT, then G of TV equal to 0. G of TV equal to 0. What does it mean? This implies T prime G of V equal to 0 for every V, which implies T prime G equal to 0 for every G belonging to range of T. This is what we have. This is the connection that we have. Therefore, G belongs to the null space of T prime. And one can easily check that this relationship works in the backward direction. What you can have is this, and then go to the definition, and this gives, and therefore any T, any G belonging to NT prime is in G belonging to RT is an annihilator of RT. Therefore, we have the connection between them. So, RT prime, RT annihilator is equal to N. So, there is a connection between these two. So, this is also equal to N prime. Okay, so that's the connection that you establish. There is a similar connection that you can establish between them. So I just write down the theorem, and the spin-off from this is that we also expect, I mean that is expected. So you see, you have T and T prime we have already explored. So if the space is finite dimensional, then we are going to observe that the matrix of T and the matrix of T prime are related by the transposition. And we already have a result that the column rank or the column rank of a matrix A is the row rank of the same matrix. But then the column rank of A is also the column rank of A prime. So there is a connection between the two, and that's the most interesting aspect. So this eventually leads to the conclusion that both T and T prime have the same rank. Okay, so we can also prove rank of T. So let us write down all these results in the form of a theorem. Okay. Over the field. Let T be a linear transformation from B to then the null space of T, then the null space of T prime denoted by is the annihilator of range of T, that is RT when that's one result. Now we have some precise information about the rank of T and the null space of T, because we are talking about the dimensions of RT and NT, or even rank of T and rank of T prime, etc. So we can work you will have to work in a finite dimensional spaces, and that is where it is defined. So for this part is concerned, we are not making any assumption that V and W are finite dimensional. But for this part, now we make if V and W are finite dimensional, with dimension of V equal to n, dimension of W equal to m, and all other things are as given, and T belonging to L, V, W. Then we have the first statement is that rank of T prime, both T and T prime have the same rank. The second statement is that the range of T prime equal to the annihilator of the null space of T. This is the relation that I have shown. See, this is the range of, this is also equal to the range of T prime. Okay? So the annihilator of the null space of T is the range of T prime. So we also look at the relation between what happens to the annihilator. The annihilator becomes larger when the corresponding space, for instance, if M shrinks, then M naught, that is the annihilator of M, becomes larger. If M enlarges, then the annihilator becomes smaller. And the extreme case is that when M consists of only the zero vector, then M naught is the whole space. Whereas if M is the whole space, then M naught consists of only the zero vector. So these are the connection between the two. Okay. So these are expected results. That's what we just explored. Okay. I think the first result we have proved already. Okay. Anyway, let us repeat the whole thing. Now what we have is that the following. Okay. So we have the relation the first thing that we want to prove is this. Annihilator that's what we want to prove. How to prove this? So we call that G of this is the relation that we have. Now, suppose G belongs to RT. Then what happens if G belongs to RT naught, that is an annihilator of RT, then that is G is an annihilator of RT. Then this implies G of belonging to V. Okay? What does that mean? That implies T prime of G of V equal to 0. Which implies G belongs to T prime of G equal to 0. Which implies G belongs to the null space of. So every element of that is RT 0 is contained in Now we work backward. Suppose G belongs to NT. Then T prime of G equal to 0. Which implies T prime G of V equal to 0 for every, which implies what? See, we apply the relation. So what happens? The definition of T, the connected with T. Then what do you get? T of G of for every. What does it mean? This implies G belongs to RT. That is, G is an annihilator of RT. Therefore, we have the following. Therefore, we have NT prime contained in RT. So together these two, hence we have so that way. Now what we are going to assume is that these are all finite dimensional spaces. For the rest of the results, we require the finite dimensionality of V and W. Now assume both V and W are dimensional and dimension of V equal to n, dimension of This is the assumption. Okay, now we are trying to prove this result, namely rank of T prime equal to rank of. So our what we want to prove is rank of equal to this is what we want. So we said that is the rank of T is the dimension of the range of T. We said or let R be equal to rank of T. Now we have RT annihilator equal to the null space of T prime. But dimension of RT annihilator is equal to M minus R. Okay, so we have the earlier made the statements of the connection between the dimensions of a subspace with its annihilator. Therefore, this is equal to this. Now we have dimension of RT prime plus dimension of the null space of T prime equal to the dimension of W. Okay. So, but we already know the dimension of okay. So we have dimension of RT prime plus what is dimension of NT prime? Dimension of, we have already seen that NT prime can be identified as RT. This is equal to M minus R, and that's equal to M. Here we are using the fact that RT prime which we have proved already. Okay. Therefore, that implies what? Dimension of RT prime equal to, that is rank of so that completes the proof. Okay. Now what else? Now we want to prove the second one. So we want to prove the next statement. Let me take out this. So what you want to prove is this. The next statement is that the null space of T, annihilator of that is equal to right T. Let us prove this. So we start with an F belonging to, this is the statement that we wanted to, I have put it in the box. Now let F belong to R. What I mean is that I am taking an F which is equal to T prime G for some G belonging to W prime. That is F is equal to W prime. That's the meaning of that. Now F of V is then equal to, F belongs to RT prime. Therefore this is equal to T prime of G of V, which is equal to G of if V belongs to the null space of T, then equal to 0. Hence, for V belonging to the null space of T, we have F of V equal to G0 equal to 0, which implies F belongs to. So one part we have proved. What does it mean? It means that RT prime is contained in LT. So we have proved one part of the inequality. Okay. Now we have to conclude that they are the same. How do we do that? We use the dimensional analysis. So what you have proved is the following. That means RT prime is a part of NT annihilator. Okay. Now we want to say that they are the same. Okay. So let us do that. So you make the following observation. Dimension of RT prime is equal to rank of T prime. This is simply the definition. And dimension of NT annihilator is equal to n minus what is called the dimension of NT. And that's equal to n minus dimension of NT equal to dimension of RT. Why? Because dimension of NT plus dimension of RT equal to n. Therefore, this is equal to dimension of RT. And that is equal to, because both T and T prime have the same rank. This is equal to dimension of RT prime. Okay. So what does it mean? Both nt prime, the dimension of nt annihilator is equal to dimension of rt prime. Therefore, nt annihilator is a subspace of therefore rt prime is a subspace of nt annihilator of the same dimension. Same dimensions. That's what we have. Okay. So rt prime is already a subspace of nt annihilator. Because of this, it follows that rt prime is essentially equal to. So that allows us to conclude the following. Therefore, which implies so that comes okay. That's fine. Now we want to look at the consequences. See, one of the interesting consequences of this is a solution to the what is called Fredon alternative theorem. Okay. Let me just look at this scenario. Okay, let us look at this scenario. We'll make some plans. First remark that I want to make, the consequence of this result is that suppose we have the following equations. Now you can conceive this as B. So you can rewrite this in this form. This can be rewritten as A of x. So the problem that you have here is, given B, does there exist an x such that Ax equal to? So given B belonging to R2, such that and a larger question is, or if yes, is it unique? Because B belongs to. Now you see see that at the outset itself, that is that the solution exists only if B belongs to the range of A. The range of okay. But we know that the range of A is equal to the null space of A, annihilated. That's what you have. Range of A is equal to null space of A prime annihilated, A transpose annihilated. Sorry. Range of A annihilated is equal to null space of A prime. This is the connection that we have. Okay. Right? Therefore, the range of A annihilated being equal to the null space of A prime, what you should have is that for G belonging to N A prime, we should have G of equal to 0. Okay. What is A prime? A prime is represented by A11, the transpose of A, that is equal to A11, A21, A12. This is given by this. Okay. So, you see that if G is equal to G1, G2, then this is what you will get. Okay. So if G is equal to G2, then this is again in R2. Okay. Then what you have is this A11 G1 plus A so G1 and G2 are the solutions of these equations. Okay. So G1, G2 or G equal to 0. So what does our statement say? Our statement says that B should be, cannot be arbitrary, but should be such that G of B equals 0 for every G belonging to null space of A. That is satisfying for every G satisfying the equation star, we should have g of d equal to 0. Okay, so that is easy to work out because you can find set of general conditions for find g1 and g2 such that they are solutions of the transposed equation. Okay, and then for those solutions, what is GB? GB is, we know, is this relation. What is that? G1 so only for G1 and G2 such that G1 B1 plus G2 B2 equal to 0, where G1 comma G2 is a solution of the equation as a solution. That's a very interesting, useful application of this theorem. In fact, you can generalize it. Okay, to space R2 for matrices and by n matrices. This can be generalized. That's an application. Another remark I want to make is the second statement that you have. Second statement says that the range of T prime so we get a complete clear-cut estimate of the range of T prime. So it is the annihilator of the null space of T. So it's easy to find out the null space of T and then get the annihilator. And more, especially if NT equal to then this is one of the another. Now this part, these results have relevance in the context of what is called the Fredholm alternative. And which, as and when you come across, you will observe this result coming. Now we prove another theorem, and there is again a repetition of the same thing. That is the column rank of A equal to the row rank of H. Using these ideas, we are proving this result. So theorem, this is the theorem which we have already proved, that A belongs to then row rank of So let us give an alternative proof of this. The proof of this is, what we do is, we choose and the BW standard based on now we define for x1, x2, etc., xn belonging to fn define P from M by P of where yi equal to sigma j equal to 1 to n aij xj, where I equal to 1 so T is now defined from Fn to Fr. Now we observe that the column rank A is equal to rank of T. Why it is the rank of T? Because you see that the rank of T is spanned by, or the range of T is spanned by the columns of A from the definition. Therefore, the column rank of A equal to the rank of T, that is the dimension of the range of T. Okay. Now, T prime is represented by A transpose. This T transpose is represented by A transpose, and this belongs to A M plus you remember it is the map from W prime to V prime. Okay. Therefore, from this you have A prime is equal to rank of T prime, which is equal to the row rank of or I will put it this way, this is the same as, or I put it in a different way, it's more like row rank of row rank of A prime, which is equal to this step is on account of the fact that A prime is obtained by interchanging the rows and columns of A. Therefore, the row rank of A becomes the column rank of A prime. And that's equal to rank of T prime by the same argument that we have used in the previous step. So what does this say? But we know that rank of T prime. Therefore, you get row rank of so that completes the proof. Now what we try to do is an alternative proof of the connection between the matrix representation of T and the in two different ordered bases. So let us start with that. So we look at an example and through which we actually prove this result, connected through the matrices and so on. So let me do that. Okay. Look at the following example. This gives an alternative proof of the relation between matrix representations of T belonging to in terms of two different ordered bases. Okay. So let us work this out. So we take let V be a vector space dimension let be an ordered basis of P. Then we have the following: PVJ equal to sigma I equal to 1 to n Aij Pi, where Aij is the ith coordinate of That's the standard expression. So that actually defines the matrix representation of T. So Aij's will be the ijth element of the matrix representation of T with respect to the basis. That is A equal to Aij. This is equal to the matrix representation of T with reference to ordered basis T. Let defined by designated by B prime which is dual to the ordered basis. Then what you have is this: Aij is essentially equal to Fi of T. This is using the property that Fi this is the one that you understand. Now let B be the matrix of T prime. Sorry. T Okay, let me just set the second order basis. So let B prime designate an ordered basis of B again, whose dual basis is designated as Fn prime, such that then what you have is this, that is Bij. Let B be the matrix representation of T with respect to B prime. Then B equal to Bij, where Bij is equal to F prime Fi prime of E T prime. This is exactly the same sort of argument connecting Aij's and Tej. Now you have two ordered bases, one V1, V2, etc. Vn. The other one is V1 prime, V2 prime, Vn prime, designated by B and B prime respectively. Now let us connect them. So we can define a linear transformation which is uniquely defined. Then we have a uniquely defined linear transformation from V to V U. Now U is from U, defined by such that U of Vj prime. Now you see it is connecting the elements of the ordered basis and then extended over the whole space through linearity. Okay. That means through linearity you can define it for every element of. Right. Now first thing that you observe is that U is why U is invertible? Because a basis onto further U transpose acts on F5 prime to give you F5. This is the connection between U transpose. Now you see U transpose is defined from on V prime, and Fi prime or the collection Fi is dual to Vi. The collection Fi prime is dual to Vi prime. Okay, so this is the relation that connects U prime and U. Okay, U prime is defined on Fi prime as Fi. So remember, U takes whereas U prime carries Fi prime. This is quite easy to verify. Okay. Therefore, and you know that U is invertible. U is invertible means U prime is also invertible. Both U and are invertible. And we also have U prime inverse equal to U inverse of prime. So the prime operation corresponds to what is called the transposition. Okay. Therefore, you have Fi prime is equal to U prime inverse of Fi. This is true for I equal to 1. And that I can replace. I can replace like this. Therefore, this is equal to U inverse prime therefore it is now right now. So we have now Bij is equal to Fi prime of T Bj prime. That follows from the earlier relation that we have. And what is called the duality or the bi-orthogonality relation. Therefore, this is equal to U inverse prime of Fi, I have used this, acting over T. That's the definition of Fi. Okay, so this gives essentially Fi of T. Let me work with this. Okay, so Fi of Tj, you write in terms of this. Okay, so what do we have? Phi of Tj prime. Okay, so that's it. Okay, the phi comes out. This is equal to Fi of Vj prime. So see, I can write this as U inverse Tu of Tj. So Vj prime will change. Okay, so this is what I get. That's Vj. That is U Fi of U inverse Tu Vj is the ijth entry of the matrix of T in the ordered basis B prime, or you have that is this is equal to B, which is equal to that's the question. Then what do you get? The next step is this. Therefore, this is equal to U with respect to B inverse the matrix of T with respect to B now this is the change of basis problem. So what we obtain is this. So B equal to the connection. Okay. So I think that's a place where we can possibly stop this talk. Thank you very much.